Hi, I'm planning several experiments that require stable temperature, so it's probably a good moment to finally build an automation for my hot plate. I'm using it for a few years already, mostly for thermotransfer, and each time I need to do the job of temperature regulator, I say to myself that one day I will finally make the proper solution for that. Well, that day just come. Better late than never. My solution is going to be quite generic, so if you have in mind using some regulated heat source, there is a good chance you will find this concept useful also in your project. So stay tuned. Here is the plan. I have my heat source, which I want to use for various purposes that require specific temperature. First of all, I need a way to interact with it from a program, so I need to build my own power regulator capable to do so. Next, I need to read the temperature from the point I am interested in. Fortunately, I already have a thermometer that is perfect for such application. I built it in this video, so you can check it out if you are curious. Finally, I need a program that will send regulation commands to power regulator basing on temperature input. Okay, at this point you may ask, why not just incorporate all those functions into one device? Well, I have good reasons to keep them separated. You see, I do a lot of different things, so I just can't predict what kind of equipment I'm gonna need next time. Probably one day I will need different heat source. With such modular construction, I can just replace it and all the other components will work as usual. I can even change power supply or method of temperature measurement. After all, it's irrelevant for other components how the temperature was measured or how the power is delivered. All what matters is that the interface remains unchanged. If you have anything in common with programming, that may sound a bit familiar. Like microservices architecture known from modern web applications, but in the world of physical devices. And this is not an accident. Later in this video you will see how useful it can be already at development stage. But first things first, let's start with adding remote control to the hot plate. A quick look inside first, just to make sure I won't blow anything up. As expected, design is rather simple. One wire goes directly to resistive element, the other goes through mechanical power regulator. Excellent, no electronic components, so I don't need to do any changes to the device itself. It should be just fine to install my regulator on power supply. For this purpose I will use triac, controlled by auto-triac. I don't want to get into details on what they are and how exactly they work, as the subject is wide and you can easily find the whole videos about it if you want to learn more. I will just say that such structure allows switching on alternating current whenever you apply direct current to auto-triac input. And this is already quite simple. Any microcontroller can do the job. Of course, I'm gonna need some current limiting resistors, and that would be it about the core concept. Time to select components. My hot plate has nominal power of 1.5 kilowatts at 230 volts, so my triac has to be able to withstand at least 7 amps. It's not much for such power component, so I will use this 600 volts 16 amps model, as it's pretty affordable and leaves me a lot of spare power if one day I would like to use stronger heater. Of course, such current will heat up also my triac. How much? In datasheet you can find on-state voltage parameter. Multiplied by expected current of 7 amps gives us approximately 9 watts of heat that needs to be dissipated. Can my triac do that? Of course not on its own. Obviously I need a radiator. I could use one like this. It has reasonable size and it's pretty cheap. Considering its thermal resistance and triac junction to mounting base thermal resistance, it should be able to keep the temperature within safe limits. But if one day I'd like to utilize full 16 amps capabilities, that can be already sufficient. So I'll spare a few bucks for a small cooling fan. For auto-triac, I will use the one with zero crossing driver, as switching few kilowatts in the middle of the wave can generate some nasty electromagnetic interference, which I can easily avoid this way. Still need some microcontroller. I like to use Wi-Fi for communication, so I will pick ESP8266 dev board this time. They become really cheap and also smaller since the last time I've been playing with them. Looks like a perfect match for such a simple project. Of course I need DC power supply for my dev board and fan. It seems ridiculous, but the cheapest 5V power sources I could find wasn't actually an open type modules, but plug type standalone devices. So I decided to use one like this, especially that I already have few of them simply lying on the bottom of a drawer. This one, for example, was for my old phone. I just need to tear it apart, and a few moments later I have 5V module for my project, for free. But I will count it anyway, so the final cost of project appears to close within €10. Pretty satisfying to me. Cool, all parts on board. Now I just need to put them all together. I will start with assembling the power part. Normally I would make PCB for it, but it's such a simple module that I decided to take different approach this time. I've seen a lot of videos with people soldering such parts directly one to another, and that seemed really straightforward for a project that consists of literally 4 elements. If you think it's a bad idea, then I guess you might be right. But you will see yourself in a few moments. So I soldered DC input wires along with limiting resistor to opto triac and attempted to solder it all to triac terminal 2. And at this point I already knew that there will be problems. Such power components are made to dissipate heat, so I had to heat it up really hard to make a proper joint. After a moment of hesitation, I finally decided to continue, as I was curious what's gonna happen. So I added limiting resistor between triac gate and second terminal of opto triac, soldered extension wires to triac terminals, and after adding few heat shrinking tubes here and there, the module was ready. Of course, with mains voltage in use, proper electric insulation is a must, so I 3D printed case for my project. I decided to use ABS filament as it has good mechanical parameters and heat resistance. Downside of ABS is that it shrinks a lot while printing, so to avoid deformations, I printed all walls separately in horizontal position, then stick them together with acetone. It creates surprisingly strong bonds, I think even stronger than those between layers. I apply some thermoconductive paste to triac pad and mount it on radiator. I also use a small stainless steel plate to install simple thermometer. It's totally optional, but I just want to make sure I have sufficient cooling. After tightening the bolt, I can add supports for radiator. I made them of 0.5mm aluminium plate, so they will act as additional heat sinks. Below I'm gonna stick 5V power supply, so I need to mark exact location of supports. Before mounting, I need to extend AC wires and install DC wires. Now I can use hot glue to fix power supply in position. As glue got solidified, I can finally mount radiator and push wires through the holes. Just a moment to bolt down cooling fan, and I can start installing the power cables. First I need to slide them through holes in front and back, then I can fasten them to the center wall. I will solder 5V power supply to input cable and use wire connector to make wiring as on diagram. Both fan and dev board will use same power supply, so I solder DC wires together and I'm ready to connect everything to microcontroller. Just a moment to secure dev board in position, and I can finally slide it all into top cover. Of course, I still need a program to handle all the necessary functions. Fortunately, due to modular design of this project, I don't need to implement any fancy logic on microcontroller side. I just need a simple function that will keep triac on to off time proportional to power set point. And as I'm using Stargate, I don't need to worry about all the complexities of wireless data transfer or user interface. So my code can be really short and straightforward. By the way, all the code I'm using in this video, as well as 3D models, are available on Stargate page. You can download the package in do-it-yourself section just below the video. On the page you can also find all the information about Stargate system if you would like to give it a try. Link in description. I have all the libraries already installed, so I can just type in my Wi-Fi credentials and hit upload. My power regulator appeared on local server, so I can finally close the cover and check how it performs. Yeah, I'm too lazy to go to my workshop right now, so I use what is available. Technically it doesn't make any difference. Especially that straight away you can see something is wrong here. Half of the nominal power goes through my device, even though it's off. At least something is working. If I switch it on, power goes up to nominal value. But obviously I can't leave it like this. I'm pretty sure I know where is the problem, but let's confirm it with oscilloscope. I will just mount some fake load and check the voltage on it. Yep, as expected. This is how half success looks like. I can control the power, but only the bottom half. Most probably I just overheated one of SCRs during soldering, either on triac or more likely on opto-triac side. Whatever actually happened, result is still the same. That's crap. Let's get back to methods I'm more familiar with. So this time I made a small PCB to accommodate opto-triac and limiting resistors. To make my life easier during assembly, I installed relevant terminals, and in my humble opinion, this time it looks more reliable. I added markings to avoid mismatching triac terminals. A quick tip for those of you who never play with triacs. Generally, with AC current, it pretty much doesn't matter if you connect it like this, or the opposite way, or change these wires, but if you switch the terminal, it simply won't work. So still you need to pay attention to the wiring. I also need some extension wires on triac, but this time I operate far away from semiconductor, so soldering is quite easy. Some heat shrinking tubes for finish, and I can reassemble my power regulator. Okay, the moment of truth. Will it work this time? So far so good, at least it's able to block the current. Let's switch it on. Perfect. This time it's a full success. Let's set some intermediate value. Okay, looks that also works as expected. So my cheap electric kettle just gained this fancy function of keeping the water warm. But I guess I will find a better use for this power regulator. Also, cooling appears to be way above sufficient. Triac temperature raised just a few degrees above ambient, so I'm quite confident that it can handle also the full load of 16 amps. Great, no remarks to the hardware, time to start working on temperature regulator. Okay, so what's the problem with this one? Isn't it enough to just switch on the heater and then switch it off when temperature raise above the set point? Well, that depends on how accurate you expect it to be. Let me show you what I mean. I will put my thermometer on top of hot plate and switch on the power for some time to check how it behaves. I will just start another process that will save the data as CSV files so I can process them later in Excel. Just a moment for piping values I'm interested in and I can start the whole thing up. As you can see, reaction is far from immediate. That's because heat is delivered to heating element which is inside the device, so it takes some time for temperature to propagate to the surface. Here are the results. It took more than 20 seconds after switching the power on to observe the first signs of temperature raise. Things get even more funny after switching the power off. It took more than a minute before temperature stopped rising. So if that would be my set point, it would be exceeded by more than 60 degrees. So if I want my regulator to be accurate, I need to figure out a bit more sophisticated solution. But there is another problem. This simple test took more than 5 minutes. But to retry it, I would need to wait for another 20 minutes before my hot plate cools down. If you ever tried to develop a solution with some level of complexity, then for sure you know that it usually requires a lot of attempts to finally make it working as it should. If I don't want to get all the working on this project, I need something faster than that. And here comes the first advantage of modular design. My temperature regulator will be a standalone program, so it don't need a physical device to work. It just needs something that behaves like such. So I can write another program that will simulate physical device, but with functions unavailable in real world, like reset or time compression. Of course, if it's supposed to save me some time, then I can't spend days implementing proper physical model. Instead, I will go with some simplified algorithm. I will introduce several layers, each one having its individual temperature. First layer will represent internal temperature of heating element, last one temperature observed on the thermometer. On each subsequent iteration, I will increase first layer temperature proportionally to current power set point and redistribute heat throughout the following layers. Finally, I will dissipate a portion of heat from the last layer proportionally to actual temperature difference to the ambient. The code is fairly simple, now I just need to adjust parameters to get desired characteristics. After a few moments of playing, I finally received something that looks pretty similar to what I recorded during test run. Should be good enough for testing my temperature regulator during development. As expected, I had to try several conceptions before I finally found one able to match my expectations. So if I had no option to perform lots of tests quickly, it would really take ages. This way it was pretty much painless, especially that I could use JavaScript instead of C++. Of course, I still need to test it on real device, but first let me briefly explain how it works. We have power, temperature and set point. Around set point there is a space I call stable range, by default plus minus 15 degrees. Because stabilizing temperature is completely different thing than heating it up somewhere close to set point, in this area I use run-up regulator logic, here stabilizing regulator logic, and if temperature goes above stable range, I simply switch off the power. In order to get to desired temperature as quickly as possible, I set full power initially. Of course, I need to switch it off way before reaching set point if I don't want to end up high above it. For that, I have cutoff threshold parameter specified in config. Before setting the power, logic will check temperature difference to set point and calculate the temperature at which the power will be switched off. Then I just wait and see what's gonna happen. If the temperature reaches stable range, good for me. But it can happen otherwise, so in background I observe the slope. If it falls below stable slope parameter, I repeat the entire process. When I finally reach the stable range, first I wait until the temperature is below set point and not rising, or it's falling faster than stable slope. In such conditions, I can start the heater. Obviously I don't know yet how much power I need to keep the temperature stable, so I need to assume something. For this purpose, I have power coefficient defined in config to estimate initial value. It doesn't need to be precise, the rest of the logic will adjust the power as needed, but the more accurate it is, the more stable temperature will be from the very beginning. As my system needs a lot of time for reaction, it is pointless to do further adjustments before the previous one could have influenced the temperature. That's why I specified reaction delay parameter, which determines how often power changes can be made. In this case, once 30 seconds. Now the only thing left is to observe what's going on and adjust the power if necessary. If the temperature is within the channel specified by set point and measurement accuracy, or the slope points towards set point, I consider everything is fine, so no need to do any adjustments. But if the slope points outside of set point, I need to take action proportional to how fast it happens. Fine, so let's finally see it in action. To make this test more relevant, I will put on top of my hot plate 2 pieces of soldering wire. This one is lead based, so should have melting point somewhere around 190 centigrades. The other one is lead free, so should melt at around 220. Of course, such placement of thermocouple does not guarantee that measured temperature will be exactly the same as here. But it's not the most important thing in this test, so for now I don't need greater precision. So let's start with 150 degrees. Okay, that looks good. Temperature seems pretty stable, soldering wires still intact. Let's try 180. Cool, lead-based solder already gave up. Looks it was really on its edge with previous set point. A few moments, and around 25 degrees later, also lead-free tin got melt. Okay, means I have some 40 to 50 degrees deviation between indicated and actual temperature, but that was to be expected with such sloppy installation of thermocouple. But all in all, I'm still happy with the result, as it proves the automation works pretty well. Hit like if you like the result as well, or subscribe my channel if you want to see what can be done with stuff like this at home. I'm planning to put it in good use soon. Thanks for watching and see you on other videos.